MCP, or Model Context Protocol, runs on a simple client-server model where an MCP host, an AI application like VS Code or Claude Desktop, establishes connections to one or more MCP servers. Imagine the client as a personal assistant and the server as its toolbox. The assistant knows what needs to be done and reaches into the toolbox to get the right tools and resources before taking an action. Clients are AI applications like Claude Code, GitHub Copilot, or support bots. They know what they need, like give me a list of issues assigned to me or run this SQL query, but they rely on servers to fetch the information. Servers are where the tools and data live. Tools are functions the AI can call, such as create issue or get issue. Resources are data sources such as CSV files, emails, databases, or code repositories. Prompts are templates that guide how the AI interprets or communicates information. For example, Visual Studio Code acts as an MCP host. When it connects to an MCP server, such as the GitHub MCP server, the VS Code runtime creates an MCP client object to manage that connection. If VS Code then connects to another server, like a local file system MCP server, it creates a separate client object for that connection. In this way, each MCP client maintains a one-to-one relationship with its corresponding MCP server. MCP is built on two main layers, the data layer and the transport layer. The data layer defines how clients and servers communicate using JSON RPC-based protocol. It covers lifecycle management and the core building blocks of MCP, that is tools, resources, prompts, and notifications. Using a protocol like JSON RPC, clients and servers speak the same language. This makes AI integrations plug and play, swap servers or tools, and everything keeps working. The transport layer handles how that communication travels, managing connections, authentication between clients and servers, and message delivery. Think of the data layer as the language and the transport layer as the delivery system. MCP supports two transport options, depending on where the client and server are running. When both are on the same machine, MCP uses standard I/O transport, which relies on standard input and output streams for fast, local communication without any network overhead. When the MCP server and client run on different machines, MCP uses streamable HTTP transport. This method relies on HTTP POST requests with optional server-sent events for remote communication. It supports authentication through bearer tokens, API keys, or OAuth for secure access. Together, these layers make MCP flexible, secure, and ready for both local and cloud integrations. Let's see a practical example. Imagine using an AI testing assistant powered by MCP. It connects to a test management MCP server such as Jira or TestRail. The assistant calls a tool like Fetch Test Results to pull the latest automation outcomes. The server returns structured data, which the AI analyzes using a predefined prompt to analyze failures, identify flaky tests, and suggest areas for improvement. Then, it triggers another tool like Create Bug to log detailed defect reports directly into Jira. All this happens without any manual step, just standardized, seamless communication between the AI and your testing tools. In essence, MCP provides a unified architecture that connects AI clients and external systems through well-defined tools, resources, and prompts, all powered by a structured data layer and secure transport layer. It's this foundation that makes MCP so powerful, transforming complex integrations into simple, standardized connections between AI and the systems it interacts with. If you enjoyed this video, please like and subscribe for more real-world AI tips for software testers. Happy testing!